So, hey everyone, you can just say hi in the comments. I can see your comments right now. Yeah, so I've named the talk The Rusty Dinosaur. We're actually talking about Deno, if no one got the hint. Yeah, so a lot of Deno is actually implemented in Rust. It's a JS runtime. So we're going to take a look at actually implementing a web API, one that doesn't yet exist in the specs, in Deno itself with Rust. So a little bit more about me is, as Maya mentioned, I'm a colleague of hers at Luno. So I do web stuff mostly. I've been using Rust for a while, kind of on and off, some WASM-specific stuff with Rust, which I have been getting back into it in some open source contributions. You can find me on Twitter and GitHub. It's both at Duncan. And then if you're feeling a little nerdy, here's my PGP fingerprint for my key. So if you want to send me encrypted mail, please do so. If you have any questions about the talk, please don't hesitate to contact me on Twitter as well. Okay, so maybe just a primer on what is Deno. So probably came on the scene about 3 years ago, but if you still haven't heard about it, it's a simple, modern, and secure runtime for JavaScript and TypeScript that uses V8 and is built in Rust. So TypeScript is supported out of the box, so it will pre-compile to JS and then run that JS. There are no project-specific dependencies, so this might seem a little weird if you're coming from like Node or actually any other NPM-managed JavaScript project. So there is no package JSON that you need to worry about or Node modules that are specific to the project. Instead, Deno actually uses native ES module import syntax and to either import a local file in a project or from any other URL. These types of dependencies are then cached, and versioning is actually handled by semantic versioning within the URL string itself. The one nice thing about Deno as well is the Deno executable is actually distributed as a single executable. There's no other dependencies. It's all self-contained. And then the one thing that they sort of pride themselves in doing is always going the web standards route. So using web streams over like their own stream implementation, and yeah, just also helping push the web forward, which is really great. And it also has a compat mode flag, which enables compatibility with Node.js. So if you do have Node.js specific packages that you still want to be able to run with Deno, you can. This support isn't 100%, but it's getting better every day. If you do notice any issues when trying to use it, then you can always open an issue on the Deno project, and everyone's happy to help. All right, taking a look at a very small sort of focused view on the Deno architecture. There's obviously a lot more crates to this than what's displayed here. But so you could call this the anatomy of a rusty dinosaur. So it's some of the stuff we'll need to know a little bit more about for this talk. So the CLI crate is probably what you're most used to with Deno. So that's the actual single executable that you can pass subcommands to and actually run your JS files and TS files. So yeah, that's the actual Deno executable, and it provides all the user-facing APIs. So core is actually responsible for the creation of V8 context. So it implements all the V8 bindings between Rust for Deno, and it also implements the JS runtime. So the runtime crate exposes the main worker API. So in Deno, in each Deno program, there's one worker, and there's at least one worker, which would be the main worker, and then that can spawn other workers further down the line. Yeah, and then that API also encapsulates the JS runtime. And then we have a bunch of extension crates. We'll be looking at extension web for our web API, but there's a lot. It's like crypto for web crypto APIs for digests and subtle crypto and things like that. Yeah, so it contains JS and the Rust ops for that functionality for the APIs. So a quick look at the JS runtime struct. So this is defined within Deno. Every runtime is associated with a V8 isolate. When we talk about a V8 isolate, it's an instance in V8 with its own heap and garbage collector. And when we talk about an owned isolate, that has implemented drops, so that when it goes out of scope, so the owned isolate actually gets disposed when it goes out of scope. And then we have a snapshot creator. So this is just a helper to take a snapshot of the V8 heap during the build process for the runtime. And then extensions. This is probably quite important for this talk. Yeah, it's just it contains the JS files and the Rust ops that adds functionality for the different web APIs to the JS runtime. And then I've just removed a few of the fields that we're not going to go into right now. They're not super important. So then in Deno CLI build, this happens when you actually build the CLI crate. We create a new JS runtime. We pass it runtime options. Will snapshot is the most important here, and that's basically prepares the JS runtime and its own V8 isolate to be snapshot. And snapshotting is basically just a process of serializing the V8 heap into a binary format that we can include in the Deno executable itself, and that can be used to recreate the V8 heap at a later time. So it allows quick startup times. You don't need to initialize an isolate from scratch each time. Yeah, so when the Deno CLI is shipped to you, it already contains this snapshot to get going within it. So now if we just take a look further down in build.rs create snapshot, then we'll just call the snapshot method on JS runtime. We'll get a slice from that, and then we just write that to the snapshot path that will be used later on in the build process to include in the executable. All right, and down to our web API. So this is what we're actually going to be implementing in Deno. It doesn't exist in Deno currently. It's not part of the proposals process. It was actually, it's actually in a draft proposed by one of the Deno core maintainers. And it's similar to text encoder, except we're not working with text encoding. So you might have come across a use case where you want to basically have a binary encoder or decoder. I'll explain the one use case or the one use that I needed for it. So here we can take in a uint8 array, maybe from a file, and we pass it to crypto.digest. We want to get the SHA-256 hash of that file. So we get the digest, but the digest byte is actually still a uint8 array. We want to get a string representation in hexadecimal. So we can create a new binary encoder. We pass the encoding hex there, and then we can encode the digest bytes. And then digest itself will be a string representation. So it will be the normal hexadecimal SHA-256 that you're used to seeing. And then on the decoder side, so this is one use case in a recent Lunar hackathon. We were implementing WebAuth in, and we'd get a base64 encoded challenge from backend, so that they'd send in a response. And then in order to use it in the WebAuth in API on the front end, we actually need to convert that to a uint8 array. And obviously, you get your standard functions that you can just take a peek at on Stack Overflow and see, how to convert between base64 and uint8 arrays. But I was kind of disappointed to find out the web didn't have, something lying around as a web API. And this sort of solves that problem where you create a new binary decoder. We specify the base64 encoding, and then we just decode the string, the FIDO challenge string, and then we'll actually challenge data will then just be a uint8 array out. So that's what we're doing today. We're actually going to focus just on binary decoder and the base64 side. The rest is quite similar. Yeah, and you can imagine how it can be done. Otherwise, you can just ask me a question on Twitter afterwards if we don't get to the questions time. So specifically, I mentioned we're going to look in the web extension crates. So this is a crate that implements event, text encoder, text decoder, file APIs, and a few other things for Deno. We're going to add binary decoder to that. So yeah, binary encoder is done similarly. So you'll see within the lib.rs of the web extension crate, it has an init function, and that's actually invoked during the runtime build and snapshot process that we mentioned before. If you go, we're actually building the extension here, so we can specify all the JS files that need to be part of the extension. So they're going to be embedded, and then during the init process, they're actually going to make sure that all the classes in there are declared during the runtime bootstrap process, and that everything's available when we start Deno. So yeah, basically here we just want to add an extra JS file, binary encoding. There's a few others that are for like text encoder, text decoder, and file APIs. Then the next thing that we have in the builder pattern is we have op encoding binary decode. So this is basically a pair that maps the string name of the op to the actual Rust op that we're going to look at in a little bit. And then just some state-specific stuff that's not super important for what we're doing now. It's state for the extension. And then we just build that extension. If we take a look at the Rust decode op, so this will still be in lib.rs, just a bit further down. We just got to define a binary decode options struct. So usually they have a few other things in here, maybe streaming when they add streaming to this API. But for now, we just have an encoding string, and I just left it as a string to be to make it clear when we match against it later. So if we look at the op encoding binary decode, you usually pass state around, but we don't require any. We don't need to interact with this op states at the moment, so we can just leave it as an underscore. I just wanted to leave it here so that we could see generally what parameters these take. And then input will be a string, so that will be like an example I showed, your base64 string. And then options is we do also pass that from the JS side, and that will give the encoding that we actually want to decode from. So then it will return a result, and the bytes that we get from decoding will create a zero copy buffer from that. You'll see in a bit. So let binary decode options, we're just extracting the encoding from the option struct. And we'll match just against the string. We're going to get base64. We're not going to do hex and base64 URL. That can be done similarly. Then we'll just create a config. So this is from the base64 crate. We're just using the standard character set. And then we'll return our zero copy buffer. And we're going to create that from decode config, passing in our input. All right, now we're on the JS side of things. So if you thought this was only going to be Rust, then I'm very sorry. So yeah, this is the immediately invoked function expression that is in our newly created JS file. So when this gets loaded into the runtime, it will immediately execute and declare our classes and make sure that everything's in the everything's defined for usage when we actually run Deno. So looking at core, Deno.core basically allows us to use the ops that we have defined. So according to that op pair, so we'll have that string name, and that's how we can basically invoke that Rust op that we looked at earlier. WebIDL I'll get to in a moment. It's from the spec side of things. It's used for basically describing the interfaces that have to do with binary decoder in our case. And yeah, it's just to make implementing things easier from the spec. And it is a web standard now, so it's pretty cool. And then we have uint8 array and type error. We import this from primordials, and Node has something similar. This is just like the untampered, pristine classes and things in the global context that we don't want. We don't want to take one that maybe a user has tampered with down the line. So yeah, this is our pristine pool of things to use. And then binary decoder, we're going to take a closer look at soon. And then we've got this WebIDL configure prototype. And basically what it does is it sets the relevant descriptors for the prototype of the binary decoder, but it's not super important, so don't stress too much about it. And then we basically we add a binary decoder to our binary encoding property on Bootstrap so that we can load it in the main.js file later. So just maybe a quick overview of what WebIDL looks like. It's not important, but I thought it would be a little interesting. So this is what you would normally see on a spec that's defining stuff to be implemented in ECMAScript, and exposed here. We'll say, okay, we want binary decoder to be exposed on in window and workers. So yeah, you've got the interface there, the constructor. It must take a binary encoding. So binary encoding, how it was defined by Luca was just that it's an enum. It can either be like the string hex or base64 or base64 URL. So we need that parameter is required. And then we have a read-only attribute that's just set to that encoding. So if we construct it properly, then that value will basically equal what we passed in. And then we have a single method just called decode. We take in an input, which is a DOM string, and we basically return a uint8 array out of that. And WebIDL itself, IDL stands for Interface Description Language. So yeah, it specifies how ECMAScript should bind to web APIs. Yeah, so next, take a look at the JS constructor. So we can even refer back to that IDL to see what's going on. But we have the binary decoder class. So this is in that same JS file we created, binary encoding. And then we have a private property. So you see the prefixed hash. It's relatively recent in JavaScript. It means so it can only be accessed within the class. We've got our constructor, which we pass an encoding string to. And then we have this prefix for errors that can happen during construction that you normally see, like if you try, maybe you pass like the wrong argument through, and then you'll get an error, like a failed to construct error, and then it will mention what it failed to construct, in this case, binary decoder. We use another WebIDL helper, required argument. So this will assert that we are getting at least one argument. And then if not, then it will error out with the prefix failed to construct binary decoder and mention that you didn't give enough arguments or something like that. And then we have, we set encoding. We need to convert that to a DOM string in this case. That's basically just a spec compliance thing. Not going to go into it too much, but yeah, you can also get errors from that. We'll also have the same prefix. And if we look here, so this is just really a simple way of doing it. But I just said if we don't have one of these encodings passed through, so say someone passes like base 32 encoding, but we're not handling it, then we'll basically throw a type error. We'll say the encoding provided, and we'll mention what encoding they provided is not supported. So yeah, so that will also mean a failure to construct. And then we'll set that private property to encoding because we know, okay, it's good. We can construct this. And And then we get this little thing called WebIDL brand. So that's like a symbol just to make sure that we're dealing with the correct prototype later. All right, and so now we're going to look at the decode method in binary encoding. So a bit further down, we've got decode. We pass an input like a base 64 string. This is where we use the assert branded to make sure that this, which is an instance of binary decoder, is an instance of prototype, and that it has the right WebIDL brand symbol. Not super important for this talk. Const prefix. So similar to the constructor, we'll say failed to execute decode on binary decoder if we have any like errors in the WebIDL helpers. Also got another required argument. So if we don't have enough arguments, also throw. And then input, we also need to just do that conversion and make sure that everything's okay. But this is the main part of this method, and this is where all the magic happens, is we use Deno.core to the method opsync. So sync means synchronous, so we're not returning a promise or anything from here. It's going to happen synchronously as defined in the spec in Luca's spec. So yeah, we pass the string name for this op encoding binary decode. We pass the input. So that's the base 64 string that maybe we want to decode. In this case, it's still general. And then we pass the decode options object, which would be the struct on Rust side. And this basically is just the encoding that we constructed the binary decoder with. All right, and then we basically add to the global scope of the runtime. So within runtime.js main.js, we have window or worker global scope, because in the IDL we mentioned it needs to be in the window and worker global scope. We have binary decoder, and we make that property not enumerable, and we pass that from the bootstrap object, binary encoding.binary decoder. And then if we've done all that and we rebuild Deno, so I just did a release build to get an optimized build, then what we get is we can use our new binary decoder. We can pass in base 64. We can call the decode method on that. So we pass in a base 64 string, and then out we'll get a uint8 array. Yeah, and then we've added functionality to Deno that didn't exist before. Some of this example was a bit contrived and maybe not best practices in all areas, but it was just to give you like a good overview of how Deno's JS interacts with Rust, and how we can develop web API functionality in the Rust extension crates. So yeah, we did it. The binary decoder class is now available in the global scope of the Deno runtime, so we can use it like any other native API. And we also implemented the decode method on the binary decoder class. The decode method calls the op encoding binary decode op, which we implemented in Rust. And binary encoder would be done in a similar way. Yeah, that's all from me. Thanks for listening.